Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss their key ideas in simple language. And in today's episode, we are going to discuss this paper, Improving Conflict Analysis in MIP Solvers by Pseudo Boolean Reasoning. This is by Gioni, Timo, Ambros, and Jakob. Right, so let's get started. Okay, so we are going to focus on pseudo Boolean integer programs, right? So, what is this? That's basically a regular linear integer program, except that we only have binary variables, right? So there are only 1 variables, binary variables. There are no continuous variables and no general integer variables. Okay, so this is the kind of program that we are dealing with, and we're going to study some things from traditional SAT solvers, how they analyze conflicts, and we are going to try to apply to this kind of linear integer programs, pseudo Boolean linear integer programs, right? So let's see how things work out, right? So in the traditional SAT solvers, again, like we have only binary variables, and instead of for linear constraints, we have clauses, right? So what does that look like? So let's say we have some binary variable x1, right? So then we can have a clause something like this, x1 or x2, or say not of x3, right? So let's say this is like one clause, okay, and we can have more than one clause, right? So we can have this and some other clause and some other clause and so on and so forth. So this is our traditional SAT formulation, CNF based formulation, right? And how do we reach conflicts here is that let's say we are basically making some decisions and doing things, and let's say that we assigned these two parts to 0, right? So if we assign x1 equal to 0 and x2 also equal to 0, then it basically forces that this third part, remaining part, should be equal to 1, right? So which is not of x3, that means x3, not of x3 should be equal to 1, that means x3 has to be equal to 0, okay? So this entire part is 1 and x3 as a variable is equal to 0. And once we have this propagation, so this would lead to this, right? And once we have propagated the value for x3, then it would lead to propagation in some other clauses, right? So that's how we do some sort of any kind of propagation in this, okay? And how do we how do we reach conflicts is that some point of time, let's say over this constraint, we were basically doing some propagation, and eventually we reached some constraint which was something like this. So here it was 0, right? And or let's say xk, and from some other constraint which had let's say 0 here, right? And it had xk bar, not of xk, okay? So this was the issue, let's say, and so in here it propagated the xk to be equal to 0, and once we reach over here, once we propagate the value of xk over here, which is like all of this part is 0, and then if we set xk also equal to 0, then this clause is entirely false, and these clauses are in ands, right? So every clause has to be satisfied, right? So this clause has to be satisfied, this clause has to be satisfied, but eventually we reach that this clause is falsified, it's not satisfied, it's basically falsified, right? So in this case, this particular part is our conflict, and this particular part is our reason, okay? So what we do is that we try to merge these two things, right? So let's say here it is something like this clause, initially it was something like c prime or xk bar, and here this clause was something like c double prime or xk bar or xk, right? So this was the original clause, right? C prime and c double prime can have more than one variables, right? So more than one literals. So everything that I have written here is also referred as a literal. So x1, x2, x3 are variables, but over here not of x3 is a literal. So one of the literal has to be true in every clause, right? So what we are trying to what we are interested in is that we are trying to find out a conflict constraint. We want to find a conflict constraint that we want to so that we avoid we basically assign some values to these variables or some literals, right? And we want to avoid similar assignments in the future. Okay, so kind of like a cut, you can say, in linear programming, that would avoid exploring this search space again. Okay, so how do we resolve this is that clearly xk has to be either true or false, right? So one of those two has to be true. So in this way, we can over here, by resolving this two, we can say that c prime, so one of this literal in c prime has to be true, or something in c double prime has to be true, right? So we saw that what happens when both of them are zero, right? So everything in c prime is zero, that would force xk to be equal to 1, and sorry, xk bar to be equal to 1, so xk to be equal to 0, and c prime, everything, if c prime, everything in c prime double prime is also 0, then we hit conflict, right? So there is a reason and there is a conflict, and then when we basically we try to merge this two, and we arrive something like this, right? So we arrive at something like this, which is called resolution, right? So this is my resolution, and we just keep doing like that, right? So my resolve constraint, note that, right? So this is still falsified under this kind of partial assignment. Let's say this is my partial assignment of literals. Some of them I have set to 0, some of them I have set to 1, and others are just propagated, right? And some of them are still free. There are no assignments for some of those literals, right? So under this partial assignment, where we have just set x1 to 0, x2 to 0, and some more maybe partial assignments, that lead to this kind of scenario where everything in c prime is 0 and c double prime is also 0. So essentially this resolved constraint is also falsified. Resolved clause is also falsified, right? So then we treat this one as my conflict, and then we look at my partial assignment again and see what was the reason that propagated the last literal in this clause to be false, right? So we find out one more reason for that, and then we again try to resolve it. We just keep doing like that till a while, right? So when do we stop? Is that again, like I think I discussed this part in the first infeasibility analysis video. So if you haven't watched it, you can you can watch it here, right? So I basically discussed a conflict graph in which we have something called decisions, right? So let's say my first decision was x1 equal to 0. Then it led to some propagation. Then I had x2 equal to 0. Then it led to some more propagation, right? And every time I make a decision over here, right, it will lead to some propagation. And eventually, let's say over here I made a decision, and that led to this conflict over here, right? So we just keep doing this thing, resolution and by conflict, reason, and resolution, and we just keep finding clauses. So over here, note that in my resolved clause, we don't have xk at all, right? So without xk also, we have something that is falsified, and so we removed xk, and we just keep going backwards like that till we hit something from the decision level. So if something where like the last decision level, there is only one value is present in my resolved clause, right? So I think it is called FUIP, right? First unique intersection point or something. And this is again, like I have explained in detail in the previous infeasibility video, right? So if you are curious about that, then you can keep looking at it. You can go and watch it, and then come back and rewatch it. But I don't think it is required to understand what FUIP is for this video, right? So the point is that at some point of time we stop. That point of stopping is something that is a very decent resolution, a very decent cut, you can say, which will help us avoid exploring this space over and over again, right? So it will reduce search space by a lot. It will basically try to capture the assignment that led to this conflict, right? And help us not go for that particular assignment. Right, so we are not really interested in the clausal constraints, right? So we are actually interested in linear constraint, right? We have AI. Let's say I'm going to denote literals by Li. is greater or equal to b, right? So these literals can be positive or negative variables, right? So it can be xk or xk bar, where xk bar is basically like 1 minus xk, right? So every time you expand xk bar as a literal, right? So make sure that you are doing 1 minus xk. Okay, so this is my standard form, let's say. And in my standard form, let's say I have all the AI and B are integers, right? And let's say my AIs are also greater or equal to 0, right? So B is also greater or equal to 0. So why this is valid assumption? So everything can be converted into a standard form, because if my AI is negative, then I take the opposite literal, right? So if I had xk here, then I take xk bar here, and then my new AI will be positive, right? So 0 is also fine. Similarly, like, so everything on the left hand side is now non-negative, right? So coefficients are non-negative, literals are 0 and 1, so they are also non-negative. So the right hand side also will be non-negative, right? So if the right hand side is negative, then it is trivially satisfied. Okay, so we are interested, so in our clause it was very easy to find out how to identify falsified clauses, right? So in here we have something called slack. Okay, so what is slack? Slack is basically I take a partial assignment, let's say row, right? Some of them are some of the literals are set to 0, some of the literals are set to 1, and others are free, right? So I take all the coefficients AI which are not set to 0, right? So say row of I is not equal to 0. This can be the literals which are set to 1 or literals that are free. So this is the largest value the left hand side can take, and I subtract b from it, right? So this is my slack, right? So traditional meaning of slack in MIPS, right? So in linear constraint. So how do we use this slack? So two things. One is that we need to find out ways to propagate things, and other thing is that we have to find out ways to detect conflicts, right? So if it turns out that if my slack is negative, that means the largest that my left hand side can get is smaller than my right hand side, then obviously I have a conflict, right? So if slack is negative, then I have falsified my constraint, or we can say that conflict. So it turns out that it goes both way also, right? So if a constraint is falsified, then the only way it can be falsified is if the slack is negative. If the slack is not yet negative, it is 0 or positive, then there is a way to still assign free variables so that this constraint is satisfied. Okay, so that's one use of slack, and the other use of slack is to propagate literals, right? So in our clauses, we propagated when everything else was 0 except this last xk variable, and then we said that this last xk should be assigned to 1, because otherwise this entire clause will be falsified. So similarly, in our linear constraints like this, we have a way to propagate things using slacks. So how do we propagate? If let's say if the slack is less than AI, then we can say that literal I is true. Okay, so now let's go back to our SAT theory. So what we did in our SAT when we hit conflict, right? So we had a reason, right? And once we had that reason, what we did was we resolved it, right? So once we have resolved the conflict, then that resolved resolved clause become my new conflict, and we keep looping over that till we hit FUIP. Okay, and in this case this will not work completely. So let's try to see with an example, right? So this is again the example that is given in the paper. So let's say we have x1 plus x2 plus 2x3 is greater or equal to 2. Let's say my partial assignment is x1 equal to 0, and yeah, so let's say this is my partial assignment for now. And if I put x1 equal to 0, then it will propagate to saying that x3 equal to 1, right? Because x2 cannot really just satisfy it. And this propagation can also be done using the slack, right? So if the slack is less than the coefficient of a particular literal, in this case the slack will be equal to what is the slack here? If after I set x1 equal to 0, that is 1 plus 2, 3 minus 2, it is 1. The slack is 1 here, and which is less than 2, which is this coefficient. That means that this literal has to be equal to 1. Okay, so that's a propagation technique. The slack should be less than the coefficient for that literal. In that case, that literal should be equal to 1. So in this case, x3 is propagated to 1. Okay, and let's say if I have another constraint, which is x1 plus 2 x3 bar, right? So when I write x3 bar, it is actually 1 minus x3, right? So it's not just trivial x3, another simple literal, right? So when we look at the linear constraints, we have to expand this, and then we have x4 plus x5 is greater or equal to 3. Okay, so x1 equal to 0, which means this part is 0. X3 equal to 1, that means this part is also equal to 0. And we are left with two variables, x3 and x5, and the right hand side is 3. Right, so the slack is 1 plus 1, 2 minus 3, which is minus 1, and slack is negative. That means we have a conflict. Right, so this constraint under this partial assignment cannot be satisfied. It is falsified now. So this is my conflict, and this is my reason for it. Right, so why it is the reason? Because this is the one that propagated the last value of x3. Right, so without x3 propagated, this constraint is not yet falsified. Right, so once we propagate x3, then it is falsified. So this is my reason, this is my conflict, and similarly, like, let's try to resolve this. When we say resolve it, we start with the conflicting variable. It was x3. Right, so we try to remove x3. Right, so we just add this 2, right, as it is. We don't really have to do any scaling for this one because the coefficients are both 2 here. Right, so this is again like 1 minus x3. So when you expand this, you have to say minus x3, minus 2x3, and then you also have to subtract 2 from this 3. Right, so what we get as the resolved constraint is this. So x1 plus x1, you get 2 times x1 plus x2, x3 will be gone, plus x4 plus x5, and here it will be 2, and here it will be 1 because I said remove 2 from here, so it will be total 3 over here. Okay, so this is my resolved constraint, and look what happens here, that x1 equal to 0, so this part is 0, and these 3 literals are free. Okay, so what is the slack here? Slack here is 3 minus 3. So slack is 0, slack is not negative, and that basically means that there is still a way to satisfy this constraint, which is x2, x4, and x5. All 3 of them takes value 1, then it is satisfied. So unlike my clause part where my resolved constraint was always falsified, here it is not that, right? So I have a conflict, I have a reason, but the resolved constraint, after I remove x3, it is not falsified. So I can't really go through this loop because my loop involves that resolve has to be falsified, and now I treat the resolved constraint as conflict and keep doing like that. But this is not happening here. So there is another step we'll be taking. It's called reduce. Right. So there is a reason. Right. So we have for every conflict we have a reason, and we are going to reduce this reason, and then we are going to do this resolution using conflict and the reduce reason. Okay. So let's take a look at what this reduction step is. Okay. So there are 2 things we'll be looking at in this video. So one of them is called weakening. Weakening a literal, right? So when I say weaken li, literal li, all I basically have to do is just set it to 1, right? And that's it. So as long as I weaken a literal which is not falsified, right? So not something that is assigned to 0, not falsified. In that case, I do not change slack. So no change in slack. So weakening alone is not really going to be enough for me to do, make my resolved constraint falsified. I have to do something more. So weakening, but for what I want to say is that weakening is a valid operation, right? So I can take some literal and then set it to 1, and then put it like remove the corresponding coefficient and reduce something on the right hand side. So this basically changes structure of the constraint. And the second part after that, what we're going to do is called we apply cuts. Right? So once we have that weakened reason, then we are going to apply cuts on that reason, and that will help us generate a resolution which is violated, right? So there are 3 types of cuts that are discussed here in this paper, which is called strengthening, and it's also called the saturation based cut, right? The second is CG cuts, Chavatal-Gomri cuts, and this is called division based cuts. And the third one, so they said like if you are doing strengthening, if you are doing Chavatal-Gomri, then why not some other cuts in literature, which is mixed integer rounding cuts, MIR cuts. So this is actually a contribution of this paper. So if this part previously already existed in the literature. Okay, so let's look at all those things. Okay, so let's start with saturation. So this is very, very simple, right? So our constraint was AI, Li is greater or equal to B, right? And sometimes it happens that these coefficients AI are bigger than B, right? So if that corresponding, let's say A phi is greater than B or greater or equal to B, if my little phi takes value 1, then this left hand side entirely is covered, right? So it is completely satisfied. So what we can do here is that we don't need something that is bigger than B on the left hand side, right? So we can say that we are going to take minimum of AI and B, and that is my coefficient for Li. So that's simply just making strengthening, right? So some of them are bigger, and I'm just reducing them to to B at least, right? So capping them to value B, and that is like one kind of technique which is called saturation. So after you apply some weakening, right? So your right hand side would be reduced, and after those weakening, if you apply this kind of saturation, then it is sometimes effective, right? So that's the idea behind this saturation based reducing. So it is actually like in the paper they have shown that if we take a reason, right? So first, let's say if we weaken all non-falsified, all non-zero, non-falsified literals. So this can be either literals which are assigned to value 1 or free, right? So all of this, if we weaken all of these literals, and then if we do this saturation, right? So then we just look at the coefficients, and whatever coefficients are bigger than B, we make them B, right? This is totally valid, right? So because previously if this literal was 1, then the entire constraint was satisfied, and here also it is left hand side, it will become B. So if this literal is corresponding literal is 1, then this constraint is satisfied. So there is no change in validity of this constraint. It is still valid. It's just that it's better constraint. So if you do these two things, then it is guaranteed that the resolved constraint, right? So my resolved constraint is made up of conflict and my reason. So conflict was violated, and reason was the one that propagated this violation. And so it turns out that if I do this weakening plus saturation, then my resolved constraint will always be violated, which is what I wanted, right? So we wanted our resolved constraint to be violated so that we can replace this conflict by the resolved constraint. Okay, so next we are going to discuss division. Division based cuts, right? So it is very simple again. So we have EI, Li greater or equal to B, right? So what we do is let's say first of all divide everything by D, right? So this is valid operation, right? So we are dividing both sides by D, which is totally fine. And this part is greater, right? So left hand side is greater, so I can actually make it even bigger. And let's say I make this coefficients integers again, right? So when I divide things, they are no longer integer, and I now make everything integer again by sealing it, right? So I'm making it bigger. because it's on the bigger side, so I can do this, totally valid operation. And now again, like on the left hand side, everything is integer, right? So coefficients are integer, literals are integer, so I can make this right hand side also integer, seal it, right? So those of you who have studied polyhedral theory, they can easily recognize that this is simply just Chavatal-Gomri cuts, right? So Chavatal-Gomri cuts, it's basically exactly this operation. Okay, and this is what we want to do after we do some sort of weakening, right? So here we're going to use D equal to AR. So what is AR? AR is basically the coefficient of the literal that we are trying to eliminate, right? So we have LR, which resulted in literal R, which resulted in the conflict, right? That was the one that last propagated and resulted in the conflict, and it is there in our conflict and our reason. So we are trying to get rid of this LR. So we are going to use AR, the coefficient of LR in this, as our D, assuming obviously it is non-zero because it's in the reason. So yeah, that's pretty much it. So here we don't even have to weaken all the non-falsified constraint. So it turns out if we just weaken the literal which are non-falsified, and out of them, not all of them, all we have to do is the literals for which the coefficients AI, coefficients AI are not multiples of AR. So AR does not divide AI, right? So only this non-falsified literals, this plus both two conditions, right? So it has to be non-falsified and this condition should be meeting that the coefficient of AR should not divide the coefficient of that particular literal. Only those literals, if we weaken, that is kind of sufficient to reach that our resolved constraint to be falsified, right? So this has to be falsified, right? So weaken this, apply this division, and then your resolved constraint is guaranteed to be falsified. Right, so we are going to extend it a tiny little bit more, which is called MIR cuts. So in theory, it is known that they are dominating cuts over Chavatal-Gomri cuts. So we are going to use that, right? So in Chavatal-Gomri, what we did was we did AI by D, and we sealed it here, and literal Li, right? So we just summed over that, right? So let's say we divide, take out some of the literals from this. Let's say this is, previously it was all the literals. Now let's say this is I1 part, and let's say I have take some of the literals from here to I2 part, right? So in I2 part I do something different. In I2 part what I do is I still divide by D, but instead of sealing it I'll floor it. Okay, so this is basically like taking -1 in the coefficients, right? So this is seal, this is floor. Okay, and this is not enough, right? So I'm going to do something more. I'm going to take a look at now what's this. Okay, so this is kind of complex. It is fractional part of AI divided by D divided by the fractional part of B, which is my right hand side, divided by D, right? So I just add this fractional part, right? And this entire thing is my new coefficient for literal I, Li, and all of this has to be greater or equal to B by D, of course, which is sealed. Okay, so now here is the thing. When do I put something in I1 and when do I put something in I2? Mostly I'll be putting things in I1, and I'll try to compute this fraction, which is fractional part of AI by D divided by fractional part of B by D. And if this fraction is greater than 0, strictly greater than 0, and strictly less than 1, right? So it's strictly between 0 and 1, then I'll put that in I2. Otherwise I'll keep it sealed like this, right? So then if this fraction is between 0 and 1, strictly between 0 and 1, right, then I'll put it in I2, which is like, instead of sealing, I'll be flooring it, which is taking value 1 out of it and then adding something which is less than 1, right? So this coefficient is obviously smaller than if I would have just sealed it. So it is a stronger constraint, and it turns out that everything that we did for the division constraint, again same D equal to AR, right? So same D, whatever we saw in the CG cuts same guarantees hold for this MIR cuts as well, right? Except that they are stronger. So because they are stronger cuts, their resolved constraint eventually that I get, eventually whatever I settled as my final conflict resolution, final conflict constraint, right? All of these are also stronger, right? So they propagate a lot more than CG cuts, standard CG cuts. So that's pretty much the MIR cuts. Okay, so let's revisit what we have seen so far, right? So we have seen that we have, first of all, clausal constraint, which were like, made from resolving clauses, something or something or something. This is my clause, and then if I resolve it with some other clause, then I get a new clause. And this is not a linear constraint, but can be converted into a linear constraint. These are clausal constraints, right? So, and with our linear constraint, right, so we actually have to do something called reduce step in between before we go for resolution. And this reduce step was basically we have to weaken some literals, plus either we can do coefficient strengthening, which is saturation, or we can do division, which is CG cuts, or we can do MIR cuts. Any of these three operation is will help me to make sure that the resolved constraint is also violated, right? So this is what is done in this pseudo Boolean type of binary integer programs, right? So again, like I think in the previous infeasibility video, I discussed there is something called filtering step, right? So this is still applied over here as well, right? So the thing is that this constraint should not have a lot of non-zeros, it should not be too long, and the coefficients that I get AIs for the resolved constraint, right, they also should be in accordance with the the rest of the MIP, right? So it should not be super large coefficients or super low coefficients, and it should not basically cause trouble, right? So these constraints are going to be added to the linear program maybe, and propagated like that. So those things are kind of filtering steps are still necessary over here, and sometimes it turns out that we have to even do this kind of weakening to our conflicts, not just the reason part. So that also is sometimes done. And yeah, so there is this kind of clausal conflicts are there, and there are this kind of linear resolutions are there. And all of this they basically experimented on Skip, and this is technically a mixed integer programming solver, but they only experimented on pseudo Boolean integer programs, which are like taken again from the miplib library, and then they validated it. It turns out that all of this conflict analysis gives about 20 to 24% gain, right? So any of this, so it actually does not really matter which conflict analysis you do, right? So this one or all of these ones, they're kind of all roughly similar, but yeah, particularly these MIR based ones are the strongest, like in terms of the node reductions. And the point of this conflicts is that they are basically added to the program, right? So they're basically added to the model, and so they should help us propagate more and help us avoid some of this search spaces that we are trying to avoid, right? So that are leading to conflicts, right? So this is happening more in MIR cuts, base weakening, radius reductions. So yeah, this is kind of the kind of summary for it. But I think I was not really aware about all of these other parts as well. Right? So I know about this resolutions, but this weakening and saturation and division, in fact, this entire reducing part was new to me. So I hope that you also learned something new from this video. And yeah, so I think I'll see you in the next video. If you haven't yet subscribed, please subscribe so that every time I upload something, you get a notification. So see you in the next video. Bye.